In this joint work with Alexander Nikolov, we discuss some results in linear discrepancy. First, a motivating problem. We are given as input an array A of n real numbers. Let S be the array of subset sums of the elements of A arranged in increasing order. Here, we mark the elements of S on the number line. Note that elements such as 7, which are the results of two different subset sums, are only represented once. We want to find the largest gap between two consecutive terms in S. Here we see such a gap between 3 and 5, as well as 10 and 12. Before discussing the solution of the problem, we describe the relationship between it and linear discrepancy. This is best done by considering integer linear programs. These consist of three parts: the objective function, the set of constraints, and the set of integer-valued variables. Here, these variables take on the values 0 and 1. Integer linear programs are typically hard to solve, so we will only do so approximately. We will use the following standard paradigm. First, we relax the integer linear program to its corresponding linear program with variables taking real values. Next, we solve the linear program. Finally, we round the linear program solution to integer values. This can be done variable by variable. As an alternative, we can take the solution of the linear program and round all the variables simultaneously. This term represents the difference between the rounded integer solution and the linear program solution. And this is taken for each constraint. If we take the maximum over all possible values of the real value vector W, then we have the linear discrepancy. In particular, the linear discrepancy of a matrix M of dimension m by n is the largest gap between all real solutions and their closest integer counterparts. This relaxation and rounding paradigm has proven quite useful for designing approximation algorithms for hard combinatorial rounding problems. Results of Rothbas 2013 as well as Hoberg and Rothbas 2017 use this technique to obtain an additive logarithmic error for the bin packing problem, matching certain combinatorial lower bounds. For this and other reasons, we want to better understand the computational complexity of linear discrepancy and design algorithms which either solve it exactly in some restricted cases or approximately. Consider the case where m is equal to 1. Then, for any 0, 1 vector x or x prime, the matrix vector product are sums of subsets of the elements of M. The real valued vector W, which maximizes the largest gap, is achieved by taking MW to be the point in between the largest gap between two consecutive subset sums. Thus, the linear discrepancy is half the length of the largest gap. Twice the linear discrepancy is the length of the largest gap between two consecutive subset sums of the elements of M. We claim that, given an array A of n positive real numbers sorted in decreasing order, we can compute the linear discrepancy of A in linear time. This claim is actually quite surprising. Recall the definition of linear discrepancy for a one-row matrix. For a fixed W, the task of computing the linear discrepancy for M with respect to W can be polynomially reduced to the subset sum problem. Thus, one might assume that even the one-row case for linear discrepancy is NP-hard. This turns out not to be the case. Before we begin, there are two things to note. First, all elements of A are positive. However, by modifying the proof that we will soon show, it is possible to remove this restriction. See our paper for the full result, or consider this as an exercise to the viewer. Next, note that A is sorted in decreasing order. If the input array is not already sorted, doing so will take n log n time, and this time will dominate the solution for the problem. To prove the claim, we will need the following lemma. Let A be an array previously described. It contains only positive entries and is sorted in decreasing order. Then we have the following relationship between the linear discrepancy of the prefixes of A. In particular, when we consider the largest gap between two consecutive subset sums of the entries in the prefix AK, this is the larger of the current kth element and the difference between the previous largest gap and the current element. Let us apply the lemma to our example from the beginning to get a better feel of what's going on. When k is 0, the largest gap is of size 0. When k is equal to 1, we have two possible subset sums, 0 and 7. Thus, the largest gap, and equivalently twice the linear discrepancy, is 7, as we can see here. When k is equal to 2, the largest gap should be the maximum of the current entry, 5, and the difference of the previous largest gap, 7, and 5, which is 2. 5 is the larger value, so the largest gap in A2 should be the length 5. We see two such intervals, one between 0 and 5, and one between 7 and 12. When k is equal to 3, the largest gap should be the maximum of the current entry 2, and the difference between the previous largest gap, 5, and 2. This value is 3. Since 3 is larger, the largest gap in A3 should be of length 3. We indeed see two such intervals, one between 2 and 5, and one between 9 and 12. Finally, when k is equal to 4, the largest gap should be the maximum of the current entry 1, and the difference of the previous largest gap, 3, and 1, which is 2. 2 is larger, so the largest gap in A4 should be of length 2. Again, we see two such intervals, one between 3 and 5, and one between 10 and 12. Now we are ready to present the proof of the lemma. We will show that the equality holds in both directions. For the first inequality, we will show that no gap in A sub k will be greater than the maximum of the current entry, and the difference between the previous largest gap and the current entry. Consider a pair of consecutive subset sums, S sub I and S sub I plus 1, and A sub k minus 1. Their gap is at most twice the linear discrepancy of A sub k minus 1. Suppose that their gap is greater than A sub k. Then, as subsets of A sub k, they will be subdivided into at least two gaps, one of size a sub k, and the other of size s sub I plus 1 minus s sub I minus a sub k. This is, at most, twice the linear discrepancy of a sub k minus 1 minus a sub k. For the second inequality, we consider two different cases. When the current element is at least as large as the difference, and when the difference is bigger. In each case, we will show that there exists a pair of consecutive subset sums which achieves the larger gap. In the first case, the current element is at least as large as the difference. Since the elements are sorted in decreasing order, the previous element, a sub k minus 1, is greater than or equal to the current element, a sub k. Thus, 0 and a sub k are consecutive subset sums among all subset sums of the array a sub k. In the second case, the current element is less than the difference. Consider two consecutive subset sums whose gap is the largest among all consecutive subset sums in the array a sub k minus 1. Since a sub k is strictly less than the difference, the element s sub I plus a sub k is a subset sum of the current array. Suppose, for a contradiction, that s sub I plus a sub k and s sub I plus 1 are not consecutive. Then there exists another subset sum of the array a sub k which is in between, since s sub I and s sub I plus 1 were consecutive subset sums in the array a sub k minus 1, this subset sum must contain the element a sub k. Now consider the subset sum without the element a sub k, here s sub j. Note that s sub j must be a subset sum in the gap between si and si plus 1. This is impossible since s sub I and s sub I plus 1 were supposed to be consecutive. Thus, the subset sum s sub I plus a sub k and s sub I plus 1 are consecutive as subset sums of the elements in the array a sub k. Here are some other results covered in the paper. First, linear discrepancy is NP-hard, though this is not surprising since the closely related covering radius problem on lattices is pi2 hard. For an integer matrix M of dimension d by n with small constant d and entries of bounded magnitude delta, we show an exact linear discrepancy algorithm which runs in time d times n delta to the d squared plus d. Finally, for an integer matrix M of dimension m by n, we find a 2 to the n plus 1 approximation in polynomial time. The following are some directions for future work. We would like to improve the hardness result for linear discrepancy. In particular, we would like to know if it is NP-complete or, perhaps, pi2 complete, though again, the latter is more likely because of the similarity between linear discrepancy and the covering radius problem on lattices. Also, we would like to improve the gap in our approximation algorithm or show a hardness of approximation result. Finally, we would like to extend our exact algorithm for the one-dimensional case to real matrices M of dimension d by n for small constants d. In particular, we would like the algorithm to run in time polynomial in n. To show the difficulty involved in coming up with such an algorithm, we have here two figures. These are geometric representations of linear discrepancy in the case where d is equal to 2. Points on the number line become vectors in the plane. Intervals are replaced with Voronoi cells. These cells are not convex unless we're working in L2 norm. The linear discrepancy is no longer half the distance of the longest interval, but a more complicated value based on the rational points of the zonotope and the Voronoi intersection points. If you have any insight, please feel free to talk to us.